In this video, we will look at the idea of exponential decay in a context involving population. So suppose the population of a town decreased exponentially from 2000 to 2010. The given table shows the population of the town at various times since the beginning of 2000. So in the left-hand column here, we have the number of years since 2000, and we'll call that T. And then in the right-hand column, we have the population, P, and this population is a function of the number of years since 2000, and we'll let F represent that function. Since our population varies exponentially with respect to T, we expect to have a constant one-year growth factor. So anytime T increases by 1, or anytime 1 year passes, we expect this population to become some number of times as large, and that number of times as large should be constant relative to the time interval. So in this case, as T varies from 0 to 1, a change of 1 year, the population becomes 5,520 divided by 6,000 times as large. And this ratio is equal to 0.92. So anytime 1 year passes, the population becomes 0.92 times as large. In that case, this should make sense to us because the population is decreasing. So if the population becomes 0.92 times as large, it's actually becoming a little bit smaller. So anytime T changes by 1, our population becomes 0.92 times as large. Another way we could phrase that is, at the end of any 1 year interval, the population is 92% of the population at the beginning of the interval. So this 5,520 is 92% of the population 1 year before. So we can do a percent of comparison as well. Now, if the population at the end of a 1 year interval is 92% of the population at the beginning of the interval, then we lost 8% of the population. So in this case, if we only keep 92% and we started with 100%, we actually lost 8%. So we have negative 8% change. So each year that passes, the population changes by negative 8% because we're only keeping 92% of the population. Now let's use the idea of growth factors to determine some missing values in this table. So we don't know the population when T equals 3, or 3 years after the beginning of 2002. But we know the population 2 years after the beginning of 2002, and so we can imagine T increasing from 2 to 3, which is a change of 1 year. And we know that if T increases by 1, our population has to become 0.92 times as large. So the population 3 years after the beginning of 2002 should be this 5,078 times 0.92, and that gives us a value of about 4,672, roughly. Now, in a similar way, we could find the population 3.5 years after the beginning of 2002, but we're going to need to use this entry down here. So we know the population 4.5 years after. So we can think about this in a couple different ways. If we imagine T increasing from 3.5 to 4.5, that's a change of 1 year, and maybe we let X represent the population when T equals 3.5, then we know that the population will start at X and then become 0.92 times as large. And therefore, this 4,123 is equal to our starting population of X times 0.92. And therefore, that population, when T equals 3.5, is equal to 4,123 divided by 0.92. And that's approximately 4,482. So we'll just round up there. So this population here is about 4,482.